Hello everyone, now I want to present you research of the efficiency of high-level synthesis tool for FPGA based on hardware implementation of some basic algorithms for the big data analysis and management tasks. Due to rapidly increasing requirements for high-performance computing systems in accordance with such criteria as performance measured in floating point operations per second, or FLOPS, energy efficiency, flops per watt, performance per efficiency, real performance per peak performance, and area efficiency. The modern trend in development of state-of-art computing system is implementation of the distributed, reconfigurable, heterogeneous high-performance computing systems. Reconfigurable computing technology used field programmable gate array, or FPGA. The traditional procedure for development implementation of FPGA is based on the using of hardware description languages, is very time-consuming. A modern approach is to use the capabilities of high-level synthesis tools. It allows us to synthesize hardware solutions to algorithms described in high-level programming languages such as C or C++, and to verify the correct operation of the synthesized algorithm, but also to optimize hardware solution by using high-level synthesis directives. Most big data analysis and management tasks need to sort data. That's why it is necessary to accelerate sorting operations. So, the object of the current research are hardware solutions for the sorting algorithms. Now you can see a simple classification of sorting algorithm. There are the most popular types of sorting algorithms. For this research, we choose at least one of each popular type: GNOME from exchanging, heap from selection, merge from merging, and quick from partitioning. There are some useful parameters and characteristics of each chosen algorithm. GNOME algorithm sort has the worst-case performance estimate as quadratic dependence and no need additional memory. Heap sort has worse memory requirements but better performance. Merge needs a lot of memory but it has a better performance. And finally, quick sort needs additional memory as logarithmic dependence and worst-case performance as quadratic dependence. There are two main steps on research: get the performance estimation both for program and hardware solution, and then compare it according to hardware costs of synthesized devices. For CPU and FPGA testing, we used the same source code for each algorithm. For hardware solution, there is an iterative procedure of optimizing device by using high-level synthesis directives for parallelize sorting procedure and increase the performance. To get sorting device performance, HLS gives us an estimation of minimal clock period and initiation interval, the number of clock periods necessary to complete execution of the particular sorting algorithm. On this slide, you can see parameter of universal process, CPU and FPGA, which we used in this research. Using FPGA belongs to the most performance family, Vertex Ultrascale. Current model has the middle position in whole family and the best speed performance. Let's see the first performance estimation without any optimization for FPGA devices. The main result is for quick sort. You can see very bad performance result. The reason is that a quick sort is a recursive algorithm. HLS can't work with recursive algorithms, so we used a non-recursive variation of this algorithm, and that has a weak characteristic. Further research result won't include quick sort. This slide presents a hardware cost before optimization. The most interesting result is for the memory using of merge sort. This algorithm uses a lot of memory blocks, too much for a lot of FPGA devices. And now there are performance graphics of GNOME and heap sort. GNOME is on the left side and heap is on the right. Both algorithms have better result for CPU than FPGA device. Also, you can see that heap sort faster than GNOME. But let's see the next slide first. There is the merge sort performance graphic. The main result is better performance for FPGA than CPU. Also, it is the fastest algorithm of chosen ones. It is need less than 0.02 seconds to sort array with 1 million integer values. But the costs for this result a huge RAM usage. And there are the main conclusions we can make after presented research. First of all, recursive algorithms require a lot of work to implement it without recursive, and they still can have a bad performance after all. Current research proves that merge sort is a very good algorithm to sort data on FPGA. And this result is real because we can make a lot of parallel process while using this algorithm. So we can say to you the main area of the future researches. It is the parallel algorithms. Thank you for your attention.